Okay, so let's talk about the problem that we just did. It was an egg, it was falling, it had a certain amount of displacement to crash into, and we used that to find the time. So the plan was to use, zoom in here, to use the height to find the final velocity right before it actually crashes. And then if we have a certain displacement, we add that in with the velocity and the displacement, we could figure out the time it would take to slow down over that period. And then with the time and a mass and change in velocity, we could find the force. So that's how the problem was written on the Wednesday that we did it. So that was kind of the plan of what we were going to do. Another way you could look at this is to say, okay, take the height, find the final velocity, and then if we assume a certain maximum force we want to design for, then use that force and the velocity to figure out how much time that would take. That's an impulse momentum problem, basically. And then over that time, from that time, we find the displacement. Time and velocity, I guess we find the displacement. So it's basically this portion, those last three steps, either forwards or backwards. We're either assuming a displacement and calculating a force, or if we assume a maximum force, find how much displacement you would need for that force. So one direction or the other. As long as you're doing one of those, you're using that, and that makes sense. All right, so let's talk about how to actually do that. First things first, we had an egg. It was dropping 2 meters. Let me grab a green pen here. It's different from the rest. It was dropping 2 meters. That was the assumption that we made. If we're accelerating at 9.8 meters per second, we wanted the final velocity. So to do that, we could either use our how fast equation and how far equation to find the time, and then plug in the time to find the final velocity, or the combination of those two equations together gives us this. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So if we use that, plug in the values that we know, don't forget to take the square root at the end, we had a final velocity of just over 6.25 meters per second. Okay, and that's how fast it's going right before it lands. Okay, so knowing that, then we started looking at the crash. So we kind of zoomed in on this portion. This is the little zoom in portion of that. It said, okay, if it's in a container that allows a certain displacement of squish here, that allows about 3 centimeters for the egg to actually like squish and move, and depending on what's inside of it, of displacement, then how much time is that going to take to stop over that distance? So, okay, now we're coming in an initial velocity of 6.26 meters per second. The final velocity of the drop is the initial velocity of the collision, right? It's two events that we're looking at. And then the final velocity for the collision is going to be, well, 0. The egg's going to stop, right? All right, so that could give us a change in velocity, but we could also we want to get time out of this. So we could go back to that same equation and solve for acceleration, and then use acceleration, change in velocity, and time to solve for time. Or we could look at the average velocity, because distance and displacement is equal to the average velocity times time. So we rearrange that for time. Time equals d over v. The average velocity is the final plus the initial over 2, like literally taking an average. We're assuming it's slowing down smoothly over that time, which it's a fair assumption, at least for the level of detail that we need. So we got an average velocity of 3.13 meters per second. We plug that in to our time equals distance over average velocity, 0.03 meters, which is the displacement of squish that it had. And then divided by the average velocity, we got a time of just under 100th of a second, 0.009, et cetera, et cetera. I'm keeping a few extra digits so that we don't have to round to the end. And if you can hold on to those extra digits, that'll help. Okay, so now we have a time. That's how long the crash lasted, right? To go from that velocity down to 0. And we're hoping it's not going to bounce, because if it bounces, that's going to be even more. Okay, so looking back at that crash, now that we have the time and we know the change in velocity, we Googled a mass for an egg, at least on average anyway. Now we can solve for the force, because the impulse, right, force times time during that crash is equal to the change in momentum. So that really is a mass times change in